Okay, so next is the last speaker, Professor Zhang from Tongji University, College of Environmental Science and Engineering. Professor Zhang is working on pollution control by means of adsorption and oxidation. Today, her topic is characteristics and mechanisms of heavy metal and MTBE adsorption on zeolites and applications in permeable reactive barriers. So let's welcome Professor Zhang. And also, I have a note for everyone. After Zhang's speech, we have a very short closing ceremony for this online webinar. So please wait a few minutes after Professor Zhang's presentation. Okay, Professor Zhang.
Okay, thank you, Professor Gu, for your introduction. And I also would like to thank Professor Shi and Professor Tang and the committee for inviting me and organizing this wonderful ISEG webinar. And this is really my great honor to present and share my work here. And today I'm talking about the characteristics and mechanisms of heavy metal and MTBE adsorption on zeolites and applications in permeable reactive barriers. And I will introduce research background, materials and methods, absorption characteristics, mechanisms, fixed bed column performance, and then the summary. As we all know, the groundwater takes an important part in our environment, economies, and daily life. For example, over 50% of the United States population depends on groundwater for drinking water. But unfortunately, groundwater is susceptible to pollutants. So groundwater contamination has become a grave matter of concern due to the increasing industry activities, mining, smelting, etc. And in addition, the co-contamination of groundwater is common and always occurred with both organic and inorganic contaminants, which is very complex for the groundwater remediation. One example for the common inorganic and organic contaminant pairing is methyl-butyl ether, MTBE, and lead. Both of them were used as petroactives. Although the use of lead has been phased out, MTBE remains a widespread organic contaminant due to its continued use in petrol in some developing countries and regions, accounting for about 92% of its global use in 2018. And for the metals, besides the petrol additives, metals are also a kind of toxic pollutants in groundwater from various sources. So how to reduce or even remove the environmental and the health risks of groundwater remediation? So this is closely related to the source, the pathway, and the receptor. So if any one of these three disappears, the risk disappears. So you can control the source itself or cut the pathway or protect the receptors. Here I'm talking about cutting the pathway with an in situ groundwater remediation technique. So when it comes to the groundwater remediation, this figure shows the different groundwater remediation techniques applied in the Superfund in the US this year. And it can be seen that the in situ treatment methods of groundwater contamination are attracting increasing attention and have been applied with increasing frequency. The permeable reactive barrier, that is PRB, is one of the most promising in situ treatments for groundwater contamination. The barriers are filled with the materials, the reactive materials, and constructed across the flow path of a contaminant plume. As the groundwater moves through, move through the PRB, the contaminants are degraded or trapped by the reactive material inside by physical, chemical, or biological processes. And the figure on the right is the PRB in a field site under construction. And we can feel that the reaction medium is a key component of PRBs, and its selection is dependent on the nature of the target pollutants and the hydrogeological site conditions. And in this study, I used the zeolites as reactive materials. And actually, zeolites are not very common reactive materials in previous study or the practical applications. Basically, in practical applications, the ZVI, the iron, is the most frequently used reactive media due to its strong ability to degrade pollutants. But it also has obvious shortcomings because it can form precipitates and other secondary byproducts, causing the PRB clogging or falling. In comparison, adsorption is a process efficient in removing both inorganic and organic contaminants from aqueous environments. In addition, the use of adsorbents will not produce precipitates, reducing the risk of PRB clogging or falling. So we choose adsorbents as reactive media. And as far as I know, few studies have investigated the effects of organic contaminants such as MTBE on the removal of toxic metals from solution by natural or synthetic adsorbents. And basically, PRB design involves the following several steps: the preliminary assessment, the site characterization, the reactive media selection, the traceability testing, modeling and engineering design, the selection of suitable construction methods, the monitoring plan preparation, and economic evaluation. And in this study, the reactive media selection and traceability testing were mainly involved. As for the materials, as I just mentioned, we choose zeolite as the reactive medium, and specifically hydrophobic and hydrophilic zeolite, and that is clinompterolite and ZSM5. So from the table, the ZSM5 have a higher surface area, a lower pH, a higher silicon aluminum ratio, and the clinompterolite have a higher CEC value, and this is beneficial for its absorption towards cations such as metal ions. And ZSM5 has a higher affinity with organics due to its high hydrophobicity. As for the environment, firstly, we conducted the batch adsorption test to obtain the absorption capacity of zeolites and their absorption behaviors to MTBE and lead, and to evaluate the influencing factors, the mass transfer mechanisms, and the desorption features, and the regeneration of the saturated zeolites. And then we used synchrotron-based exact technique to further explore the lead adsorption mechanisms in the absence and presence of MTBE, and to examine the coordination environment of the absorbed lead on the surface of the zeolites, and also discuss the influencing factors and compare the different absorption mechanisms of lead on different zeolites in the absence and the presence of MTBE. And lastly, we used the flat column test to simulate PRB and then some parameters to evaluate the safety of to remove MTBE contamination from water. Now let's see the firstly for very for MTBE sources also sensitivity. So the T absorption was the best useful model for kinetics, indicating the chemistry. For the half absorption time, the half absorption time is typically considered as a measure of the absorption rate. And from this table, it increased with the increase in MTBE concentrations, indicating the increase in the absorption rate with the increase in MTBE concentrations. And when it comes to the absorption isotherms, the MTBE absorption can be described best by the Langmuir model, indicating a monolayer and a homogeneous absorption process. And the maximum absorption capacity, that is Q0, is about 54 milligram per gram, and the RL value indicates that the absorption is favorable. And we also make a table to compare the absorption capacities and the most suitable models for CSN5 with other absorbents. And we can see the absorption isotherms follow different models, such as the BET model, the Freundlich, and the Langmuir model, depending on different absorbent types. And among these absorbents, CSN5 have a good absorption performance, and the performance is much higher than most absorbents listed in the table, and but lower than activity carbon, modified clinoptilite, and one CSN5 in other study. And it is clear that the absorption ability of absorbents depends on not only their types, but also their own detailed physiochemical properties, such as the CC and the surface area, etc. The figure on the left shows the MTBE removal remained high, and as high as about 90%, and was hardly affected by the change of the initial solution pH. And this is beneficial for the practical application of CSN5, because this makes it conducive to changeable environmental conditions. And the figure on the right shows the desorption characteristics, and it took about 24 hours to approach desorption equilibrium, and the MTBE was hardly dissolved. And this means the absorption between CSN5 and MTBE is strong. The mass transfer process has an impact on the absorption equilibrium time, and it generally involves 4 steps: the transport from the bulk solution to the boundary layer, that is bulk diffusion, and then film diffusion, intraparticle diffusion, and the absorption on the interior surface of the solvent. And the intraparticle diffusion generally includes pore diffusion and surface diffusion. And the first and the last steps are generally considered to be very fast. So the overall absorption process is controlled by film diffusion or intraparticle diffusion. In this study, we used the Webb and the Morris model in this figure to describe the process of the intraparticle diffusion. And the figure shows that all the curve plots covering the initial phase passed through the origin here, suggesting that the intraparticle diffusion should be the rate controlling step in the removal of MTBE. That is, film diffusion may be very fast and could be ignored. But to further judge whether the pore diffusion and surface diffusion is more important, the diffusion coefficients were calculated. From this table, and we can see the pore diffusion is the rate limiting step. This is because the surface diffusion and the pore diffusion act in parallel and competitively. So the faster process determines the total absorption rate. We also evaluated the regeneration of the saturated ZSM5, and we used 6 regeneration cycles, and it was found the absorption capacity of the regenerated ZSM5 remained satisfactory after 4 regeneration cycles. As for the lead absorption on zeolites, considering the quick absorption, the absorption kinetics were not included, and we only investigated the absorption isotherms and the effect of pH and MTBE. And we can see the lead absorption on ZSM5 follows the Langmuir model with the maximum absorption capacity of 14 milligram per gram. And this is extremely lower than that of the clinoptilite, which is 95 milligram per gram. And the absorption of lead increased with the increasing pH, but MTBE has a negligible effect on lead absorption for both zeolites. This is because MTBE mainly enter the pores of the zeolites, but lead is absorbed by ion exchange and surface prediction. So they have different absorption mechanisms. As for the synchrotron-based exact technique, we used it to further investigate the coordination of the absorbed lead on the zeolite surface in the absence and presence of MTBE. And in the case of ZSM5, we found that the led to silicon surface site occupancy and the formation of the lead hydroxide surface coating are 2 main mechanisms of lead binding. And the surface coating plays a more important role at pH 6, which explains why the lead removal increased with increasing solution pH. And in the case of clinoptilite, the exact results show that both site occupancy and surface precipitation are the main lead uptake mechanisms, and the surface embedded lead uptake at the MG site on the clinoptilite surface is a secondary mechanism when MTBE is present. And finally, we made a table to comprehensively compare the lead absorption on these 2 zeolites in terms of the physiochemical properties, absorption features, and the mechanisms in the absence and presence of MTBE. In word, batch absorption test showed the excellent absorption behavior of zeolites to MTBE and lead, and their absorption mechanisms are also well figured out. So we conducted a series of fixed batch column tests to investigate their column performance and examine their application feasibility in PRB. So firstly, we investigate the sole MTBE absorption on ZSM5 in the column, and the breakthrough curve modeling was used to describe the concentration file, and we found that the dose response model is the most suitable model. And then we discussed some influencing factors such as the flow rate, the bed length, the ZSM5 dosage, and influent MTBE concentration. And we can see from the table that the column absorption capacity was found much lower than the maximum absorption capacity from the absorption isotherm modeling, as mentioned earlier. So this is mainly due to the contact time between the CSM5 and MTBE in the column is not enough, only for 461 minutes. But the adsorption equilibrium time in the batch test is about 24 hours. For the CSM dosage, a higher CSM dosage the saturation time of the column with a higher CSM5 percentage was significantly longer, and this breakthrough curve have a smaller gradients due to more available adsorption sites for MTBE removal in the column. As for the MTBE influent concentration, with the increase of the MTBE concentration, both the breakthrough time and the saturation time decreased, and the slope of the breakthrough curves between the breakthrough point and the saturate point, that is mass transfer zone, became slightly steeper. And this is because the higher concentration gradient at higher inlet MTBE concentrations caused stronger mass transfer driving force and the faster transport in the column, leading to a quicker saturation of the adsorption sites on the CSM5 surface. And another influencing factor, the bed length. The decreasing bed length lead to a faster breakthrough and saturation process, and resulting in earlier exhaustion of the bed. And this is because the longer bed length leads to the longer distance and moving time of the mass transfer zone between the two ends of the column. And on the other hand, the increase in the bed length also leads to the increasing mass of CSM5 and provide more adsorption sites for the MTBE removal. After that, we used the BDST model and obtained some kinetic parameters to predict the column performance at a new flow rate without further experimental runs. This is meaningful because the groundwater flow, the real groundwater flow through is generally between 1 to 1,000 meters per year. So this is far lower than the flow rate adopted in the experiment. So we can use BDST model to predict the column performance at a new or slower flow rate. Then we use the same way to investigate the lead and MTBE co-adsorption on mixed zeolites in the column, and the effect of green size of zeolites was also examined, and the thickness and longevity were also estimated. And the applications of materials with small particle size can reduce the hydraulic performance of the column as well as the breakthrough time, but increase the saturation time of the MTBE adsorption nearly 4 times. So from the table, the minimum thickness and its corresponding longevity also became higher by the replacement of granular clinoptilite by its powder form. So here are the conclusions. From the batch adsorption test, the best fitting of the Langmuir model and pseudo second order model suggested a monolayer and homogeneous chemi-sorption process, and 24 hours is required to reach equilibrium for both adsorption and desorption. The adsorption rate is mainly controlled by pore diffusion, and the initial solution pH has little effect on the adsorption process. And the adsorption capacity of the regenerated CSM5 remains satisfactory after up to 4 regeneration cycles. And from the synchrotron exact studies, the site occupancy and surface precipitation contribute equally to lead removal by cleanup light, while surface precipitation is the main lead removal mechanism for GSM file, followed by site occupancy. Despite the negligible effect of MTBE on observed lead removal from solution by both zeolites, a surface embedded lead removal mechanism through the empty site on the cleanoptilite surface arises when MTBE is present. And lastly, from the fixed bed column studies, the dose response model was found to best describe the breakthrough curves, and the kinetics parameters obtained from the BDST model can be employed to facilitate the full-scale design of the column at a new flow rate. And that's all my presentation. Thank you everyone for your attention. But lastly, I still want to introduce a special issue to you. And I'm now leading a special issue for the International Journal of the Environmental Research and Public Health. And the topic is application of biochar for soil remediation. So I sincerely invite everyone interested to submit a paper to this special issue, and the deadline is the end of this September. So you can scan this QR code for more information. Thank you.
Okay, thank you very much, Professor Zhang. It's a very interesting presentation, and zeolite is a very useful materials for the adsorption of heavy metals. So since we are ahead of our schedule, we don't have time for the questions. So please, if we have any questions, please emails to Professor Zhang and communicate privately. And that's all for the session this afternoon. We thank all the 6 speakers for the interesting and very useful presentations for us.